Okay, welcome back to more probability, this time the multiplication rules. And this time I'm not going to do too much annotation. Where I'm recording doesn't have a good pen, so I'm just going to try to do it without it. So, on the screen it says multi-stage experiment. Very simply, this means you're doing an experiment and you do two things back to back. For example, you might take a card out of the deck, and then the second thing you do is take another card out of the deck. The second one talks about with replacement. If we stick with the cards in a deck example, and you pull a card out of the deck, on the second card selection, you've put the card back in the deck. That's what it means with replacement. You put the card back in the deck, so you're pulling from a full deck on the second selection. Third, two events like those are independent if the probability of the second event does not change because the first event actually occurred. And we've got an example of cards. Well, a real quick one. You pull a card and say it's an ace. Then you pull another card after you've placed the ace back in. Since you've got the same cards on the second draw, they're independent because you've got the same cards to choose from. For two independent events, if they're independent, if the probability doesn't change, then the probability of both those events happening, E and F, remember this is AND. The OR probability was covered with an addition rule. This is the multiplication rule when we have an AND. So OR, you do the addition rule, and you do the multiplication rule. They also need to be independent events, otherwise we're going to have to make a bit of an adjustment. If that's the case, we can just multiply the individual probabilities to get our AND probability. Next, mutually exclusive versus independent. I think I might change the wording on this one. Mutually exclusive means you've got two events in both of these examples, not in both of these definitions. We're talking about two events, one happening right after the other. If they're mutually exclusive, they can't happen at the same time. Same time. That means they cannot happen at the same time. If they can happen at the same time, that means they're not mutually exclusive. Independent means something different. Up here, this means can they happen at the same time? Independent is talking about something else. It's talking about whether the probabilities change when you go from one event to the next. If going from one event to the next does not change the probability, they're independent. We've got a state fair example, and we've got a booth at the state fair with rubber ducks. We've got 50 rubber ducks in the pool. 3 of those rubber ducks have stars on them. We want the probability of choosing 2 ducks that both have stars on them. If we get 1 starred duck, we get a small stuffed animal. If we have 2 starred ducks, and we get an extra large stuffed animal. Since it's being replaced, our rubber duck that we pull out is being replaced, then we'll just multiply the two probabilities. They're exactly the same in both cases. And there's the probability that we get two starred ducks, one after the other, with replacement. We've got another one here, quite different. Human Resources has been keeping track and found the probabilities that employees are written up for certain infractions. We want to find the probability that a given employee is written up for three things: being late for work, for unauthorized breaks, and leaving early, all three. Now remember, we're assuming that these are independent events, so we can just multiply the individual probabilities. So here are the probabilities we're interested in: late for work, leaving early, unauthorized breaks. What's the probability that an employee is flagged for all three of those? Since the question said that they're independent events, we can just multiply all three probabilities to get the probability that an employee is written up for all three of the infractions. Do you think that employee is going to get fired? We'll see, I guess. Next, without replacement. So, first of all, when objects are not placed back, if we don't put them back in, then when we pull the second card out, we don't have the same cards to choose from that we had to begin with. When we pull the first card out of a normal deck, we have 52 cards to choose from. If we don't put that card back in, then when we make the second selection, we won't have 52 cards to choose from, we'll have 51 cards. This is an example of a dependent event because the first event happening influences the probability of the second event. So let's go back to the rubber duck booth. This time, regardless of what we do with the first duck, they're not going to put the duck back in. So what's the probability that both ducks have stars on them? On the first one, we already found that the probability on the first duck selection was 3 over 50, because we've got 3 starred ducks, 50 ducks altogether. But on the second selection, because we don't have replacement, one of those starred ducks is already gone, so we only have 2 to choose from, and there are only 49 ducks still in that small pond. So that will give us probability of getting 2 starred ducks if we do not replace the duck from one selection to another. And we can see that the probability without replacement is even smaller. Remember, the other one was 0.0036. Now without replacement, it's down to 0.24. You have an even smaller chance of getting that large, extra large stuffed animal. Conditional probability. Now you have to make sure that you keep these two straight. But if you can read this, it means the probability that this happens, F happens, some event, if this has already happened. So this happened first. It's a done deal. And we want to know the probability that if that first thing happened, what's the chance of the second one happening? Here are two formulas for you. Here's our friend probability of E and F. And that is equal to the probability of E happening all by itself times the probability that F happens, that's the second event, if E has already happened. And of course you can reverse them just like this. So let's take a look at two aces in a row from a standard deck of 52 cards. Assuming there are 4 aces, as usual, and cards are chosen this time without replacement. And we want 2 aces. There we go. We want 2 aces in a row. We're not replacing. So on the first selection, we've got 4 aces to pick from originally. We've got 52 cards in the deck. But on the second selection, because without replacement, then since we already chose a card, an ace, there are only 3 left in the deck. And there are only 51 cards left in the deck. So the probability has changed. They're dependent events because the probability has changed. And we've got a chance of 0.45%. Not very likely that we pull out 2 consecutive aces. Next, let's suppose you're a member of the Rotary Club. There's 17 newcomers, 24 long-term members. 2 members are chosen at random. So we've got 2 selections. Where's my cursor? 2 members are chosen at random, of course, to be on the scholarship committee. What's the probability of choosing 2 members at random? First being a newcomer, and the second being a long-term member. Well, first selection. There are 17 newcomers, so when we make the first selection, 17 newcomers to choose from. And we've got how many to choose from? We've got 17, 24, 41 members. That's on the first selection. When we go to make the second selection, we want to pick a long-term member. Well, there's still 24 long-term members there, but there are only 40 in those 2 categories left. You're doing one after the other, so you multiply those 2 together, and your chances are about 24.88%, or about 25%, 1 chance out of 4, roughly, that satisfy the conditions. This is another way of looking at that. Remember, this is the probability that this happens if this has already happened. If that's what you want, then you can take the probability that both happened, divide by the probability that E has already happened. Notice that this probability here and this second letter here are the same. Those are going to be the same. And up on the top of your fraction, it's going to be the probability of E and F happening. So E and F definitely on the top. This one down here is the one that's already happened. which is the second one in this statement. So here's another one to look at. You've got 300 applicants for a job, 212 are female, 210 are females who own a graduate degree. So notice, where's my cursor? There we go. These are an and statement. This is 110 females who also have graduate degrees. Female and graduate degrees. And this is just probability of, this will be the number of females. So if we want the probability that a randomly chosen applicant has a graduate degree, so the probability they have a graduate degree given that that person is female. Remember, there are 300 applicants. So if we want this, we want the probability on the top of G and F, female with a graduate degree, and on the bottom we want the one that's the given condition, which in this case is the female. Probability of a female. Okay. The probability of G and F, we have G and F right here. That'll be 110. And we've got 300 applicants. On the bottom, the probability of the person being a female. Well, there's 212 females, 212, and there are 300 applicants. Complex fraction, but the calculator can handle that. You should be able to, because if you multiply the top and the bottom by 300, you end up with 110 over 212. We'll get the results in a minute. Look at the second one. Where's my cursor? There we go. Okay, so got that one ready to go. Take a look at this one. Now for this one, we want the probability. What we're looking for is the probability. Where am I? There we go. We want the probability that an applicant is female given that they have a graduate degree. All right, on the top is always the and statement. So it's female and graduate. On the bottom is the given probability, graduate degree, probability of the graduate degree. This G and this G here agree. This and this, the G's agree. So what is it? Well, female graduates, there are 110, they're female graduates, just like the last one. The numerator is always the same. Got 300 applicants. And the given part, the probability of a graduate degree, there are, let's see, where is it? Got distracted by someone here. Oh, here we go. 152 of the applicants have graduate degrees. So the denominator will be 152. We've got 300 applicants. Again, we can reduce that to 100 over 152. reduce it if you need to. It's most likely better to just use the calculator and get a decimal answer. That way you can also give it as a percent if you want that. So there's the first one, which is about a 50-50 chance, a little bit better than a 50-50 chance that the person has a graduate degree if they're female from those applicants. And second, that the probability of there we go. The probability of female, given that it's a graduate degree, is about 72%. It's not the same. So the important thing to notice is that this is not the same as that. In unusual circumstances, it could be, but you can't calculate them the same way. Remember, the second item here is the given, and we'll have that probability on the bottom. On the top will be the and statement, and that'll lead us the way to get our correct answer. A little bit about the lottery. You can read that, pause it a second and read it. So we're back to the fundamental counting principle. You have n stages. In other words, n different things that you're doing. The first thing that you're doing can be done, where's my cursor again? There we go. The first thing can be done this number of ways. The second thing can be done this number of ways. Third one can be done this number of ways, and so on. If you want to find out how many different ways those things can be done all together, just multiply all those together, and you've got the result. We've done that before. Here's an example. So Kilby is beginning her first year, and she's going to have English, college algebra, American history, and physical science. How many different ways can she put together her first semester with those 4 subjects? Well, take 8. That's it. Takes care of the English. Multiply that by 12. If we were just looking at English and college algebra, there would be 96 ways she could select those 2 classes. But she's also got 11 American history to choose from and 5 physical science classes, for a total of 5,280 possible options for her schedule. Here's another one. Mission Statesville needs a new vice president, and secretary. The board consists of 11 members who don't already hold an office. So that's our sample space. So we're choosing from 11. Where's my cursor again? There we go. It's hard to keep track of it. So we have 11 to choose from. How many different ways can we choose those? When we make the first selection, we've got 11 people to choose from. But once we make the second selection, there's only 10 people left. We've already chosen one of those. So 110 possible ways to elect the new officers. Let's suppose Mother Robin is preparing an afternoon snack for her twins, Matthew and Lainey. She wants to give a snack of one item for each one and has the following snacks on hand. So the first thing, we want to know how many snacks there are. 1, 2, 3, 4, 5, 6, 7 different possible snacks. She chooses one snack for Matthew, one for Lainey. What's the probability each child gets the same snack as yesterday? Let's take Matthew. We'll shorten his name to Matt. If he had one of those snacks yesterday, how many snacks do we have to choose from for today? We want the probability that each child gets the same snack as yesterday. So the probability that Matt gets the same There's only one snack we can choose from if he's going to get the same one. 1 out of the 7. And for Lainey, the probability she's going to get the same snack is 1 over 7. They're independent of each other, so the probability they get the same snack very good at this. Equals 1/7 times 1/7 or 1/9. So about a 2% chance that each child will eat the same thing 2 days in a row. Not a big chance. And that's it. Well, we'll see you in 4.4. Bye for now.